안녕하십니까?
Good afternoon. This is the second day of the third GCFA. My name is Chung Ji-yeon from the Livestock Product Safety Policy Division of the MFDS. I will be leading you through today's program. It is raining outside. In spite of that, we have many people here in spite their very busy schedules. So I would like to thank all of you from both home and abroad. Also, many people are joining online as well, so thank you very much for your participation. So, like we did yesterday, we are broadcasting today's conference live on YouTube, like we did yesterday. And also, the video will be uploaded on the official conference homepage after the conference is concluded. So we had the wonderful keynote speech by Professor Park Yong-ho yesterday, and we had two sessions. The first session was efforts by international organizations to reduce AMR in the One Health approach, and we heard presentations from FAO, WHO, and OHA. And in session 2, under the theme of current status and strategies of AMR reduction in food, human, and environment, we heard from EFSA of EU, from MFDS of Korea. We heard very impressive presentations. And today, we will be having sessions on latest technologies for reduction and surveillance of AMR, and also the FAO Act project. And also we will have summary and discussion at the end. I really look forward to the content that will be shared today. So we will now begin the second day of the third GCFA, and this is session 3. Which is on the latest technology of reduction and surveillance of AMR. And let me introduce the chairperson of session 3. With the big round of applause, please welcome Kim Sun-han from the MFDS. Good morning. I am Director of Food Microbiology Division at NIFDS. And in this session, we will be learning the latest technologies for reduction and surveillance of AMR. There will be 3 presentations.
So the first presenter will be talking about the application of the whole genome sequencing for AMR monitoring program. And for this, Dr. Xiaohua Zhao from the US FDA will give us a presentation. He's a senior biomedical research and biomedical product assessment service at FDA Centers for Veterinary Medicine. She received her PhD from the University of California. And please welcome her with a big hand.
Good afternoon. First of all, I would like to thank the GCFAR committee for inviting me to give this presentation. Today, I'm going to talk about the application of whole genome sequence for AMR surveillance program. Antimicrobial resistance poses significant threats to public health worldwide. Here is the US CDC 2019 AMR report. Each year, more than 2.8 million people infected with antimicrobial resistant bacteria in the United States. More than 35 people die as a result. Antimicrobial resistant Campylobacter and non-typhoid Salmonella, 2 major foodborne pathogens, were listed as a serious threat organism. To combat antimicrobial resistance, the US government, in partnership with foreign government and organization, has developed the US National Action Plan for combating antimicrobial resistance. The plan takes a One Health approach and set up 5 strategic goals. One of the goals is to strengthen national One Health surveillance efforts to combat resistance. Another goal is to advance development and use of rapid and innovative diagnostic tests for identification and characterization of resistant bacteria. The U.S. National Antimicrobial Resistance Monitoring Program, NAMS, is working towards this goal. NAMS program was established in the 1996. It's a collaborative effort between FDA, CDC, and USDA. And 3 agencies working together to determine antimicrobial resistant profile of Campylobacter and Salmonella isolated from human, retail meat, and food animals. CDC is in charge to test all the human isolates, and FDA in charge to test the bacteria isolated from retail meats. And all the food animal isolates were tested by USDA. In addition to Campylobacter and Salmonella, FDA and CDC also tested the antimicrobial resistant profile of E. coli and enterococci. CDC tested additional organisms such as E. coli O157H7, Salmonella typhi, Shigella, and Vibrio. For FDA, since we started sampling the seafood, so we tested additional 2 organisms, Aromonas and Vibrio. Each year, we have integration final report and post our findings in the website. In order to improve the One Health surveillance program, in the last few years, we have collaboration with EPA, Environmental Protection Agency, to determine the resistant profile of bacteria isolated from surface water. We also collaborate with the veterinary laboratory investigation and the response network to determine the resistant profile of bacteria isolated from a companion animal. In the past, NAMS used several methods to characterize the bacteria isolated from a different source. We use traditional biochemical and the PCR for bacteria speciation. We also use broth microdilution to determine the resistant profile. Use traditional serology to determine Salmonella cell type. We also perform post-field gel electrophoresis, PFG, to determine bacteria clonality. When we report the trend of the resistance, very often we do not know what gene or mutation are corresponding of this phenotype. So we will take additional research to find out the resistant mechanism. We normally use PCR followed by sequence analysis to identify the gene or mutation that are responsible for those phenotypes. As you can see, this is a very tedious process and very costly. In the last 10-15 years, whole genome sequence has improved tremendously, become cheaper and faster. So we are thinking that use the whole genome sequence, maybe we can replace the multiple methods I just mentioned in my previous slide to characterize the bacteria. And before we implement the WGS to the NAMS program, we want to make sure that we will be able to detect all the resistant gene or mutation from the WGS data. And also make sure that the resistant gene are responsible for the phenotype we tested. Here is an example. This is E. coli from phenotypic testing that show resistant to 5 different antimicrobial, resistant to streptomycin, tetracycline, chlorphenicol, sulfamexazole, nalidic acid. Through the whole genome sequence, we'll identify all the gene and mutations that are responsible for each of this phenotype. So in this case, we say the phenotypic genotypic correlate 100%. So before we implemented the WGS to the NAMS program, we have conducted several pilot projects to check the correlation between phenotype and genotype for the 4 organisms. Here is a Salmonella study. In this study, we selected the 640 Salmonella that represent 43 different serotypes isolated from retail meats and human. Those Salmonella has a different resistant profile and a different PFG pattern isolated from 2011 and 2013. Through the whole genome sequence, we are able to identify 65 unique resistant genes, and plus the mutation in tooth housekeeping gene that are associated with quinolone resistance. The 65 unique genes that are responsible, they resistant to different antimicrobial classes and different antimicrobials I listed here. This slide shows the summary of the correlation between phenotypic and genotypic among the 640 Salmonella. On the left side here lists the 14 antimicrobial we tested for the phenotype. So we did the correlation, use the term sensitivity and specificity to see the correlation. Now I'd like to explain how we calculated the sensitivity and specificity. I use gentamicin as an example. Among the 640 Salmonella isolates, 105 of them show the phenotypically resistant to gentamicin. So 99 of them have carried the gentamicin resistant gene. 6 of them do not carry the gentamicin resistant gene. So 99 divided by 105, that's equal 94.3%. That is the sensitivity. Also, we call the positive correlation. Now let's look at the specificity. Among the 640 isolates, 535 show the phenotypically susceptible to gentamicin. 530 did not carry any gentamicin resistant gene. However, we have 5 isolates that carry the gentamicin resistant gene. So 530 divided by 535, that's equal 99.1%. That is the specificity. So we did this calculation for each antimicrobial. As you can see, most of the isolates has over 100. Some of them are to 100% sensitivity and specificity. So overall, we got the 98.8% sensitivity and 99.1% specificity, which is greater results than what originally we expected. And you can see some of reach 100% sensitivity and specificity. However, some of them has lower, specificity, such as streptomycin, and some of lower sensitivity, such as trimethoprim. We only have the 86.4% sensitivity. So we did the further study to wonder why some of the correlation has a lower sensitivity and specificity. So we used the streptomycin as an example. So since CSI did not establish the resistant breakpoint for streptomycin for Salmonella and E. coli. So in the past, our program has used 64 microgram per ml as a resistant breaking point for streptomycin. So in this study, we used over 600 Salmonella and E. coli. So we run the phenotypic test to show how the MIC distribution look like for the isolates that with or without the streptomycin resistant gene. So as you can see, if isolates do not carry any resistant gene, then MIC is between 2 to 16. If isolates carry the streptomycin resistant gene, the MIC will be between 16 or over greater than 64. So if we use the 64 as a resistant breaking point to do the correlation, then we will miss some of the isolates with MIC 16 or 32, but they carry the streptomycin resistant gene. So now let's look at the right side of the table. As you can see, if we use 64 as a break point, we maintain the sensitivity 100%, but the specificity only 68%. If we lower down the breakpoints to 32, we still get the 100% sensitivity, but the specificity increased to 92.6%. If we use the breakpoints to 16, now the specificity improved to 100%, but the sensitivity decreased to 97.9%. So based on this study, our program has decided to use 32 microgram per ml as a resistant break points. Streptomycin study, so we think that we can establish the user WGS to determine or establish the genomic cutoff value to measure the antimicrobial resistance. So in this study, we used over 1,700 Salmonella isolates to investigate the isolates with the gene without the antimicrobial resistant gene, how the MIC distribution look like. So here we use ciprofloxacin here as an example. So any isolates that do not carry the quinolone resistant gene, that they have the MIC equal or less than 0.06. This is over 1,600 isolates, but there's except one. And the rest of the isolates, they carry different quinolone resistant mechanism. They have MIC equal or greater than 1012 microgram per ml. So depending on what mechanism they have, they don't have different the MIC. For example, for these three isolates, they carry the double mutation in GIA. They have MIC greater than 4 microgram per ml. So we finally to look at the comparison of genomic cutoff versus the CLSI and UCAS breakpoints. Here we analyzed the 13 different antimicrobials. Here is the CLSI susceptible breakpoints. In other words, any isolates have the equal or less this value. That means they are susceptible to each of this drug. Now let's compare the GCFA. With those values equal or less this value, that means those isolates do not carry the resistant gene for those drugs. So as you can see, compare GCFA and the CLSI breakpoints, they have great correlation. Many of the values identical. Some of our GCFA value also are correlated very well with UCAS, the break value. This slide shows the pilot project to look at the phenotypic genotypic correlation on Campylobacter. In this study, we used 114 Campylobacter isolated from retail meat, human, and the food animal. And we determined the phenotype with the 9 different antimicrobial belong to 7 different classes. So through the whole genome sequence, we are able to identify the resistant gene that are responsible for each of this phenotype. Then we calculate the sensitivity and specificity just like we did on Salmonella. As you can see, many of the isolates, show the great correlation with the phenotype. And some of the drugs show the 100% sensitivity and specificity. For example, tetracycline and quinolone, these 2 drugs show the 100% sensitivity and specificity. So overall, we got the 99.2% sensitivity and specificity. So this results even better than Salmonella data. So we continue to conduct the pilot project for enterococcytes and E. coli. All of the data show the great phenotypic genotypic correlation. We published all this data in peer-reviewed journal. So if you are interested in detail of our finding, and you can read our publication I listed here. So since 2015, we have implemented WGS in the NAMS retail meat program. We sequenced every single Salmonella and Campylobacter isolated from retail meats in 2015. And in 2019, we started sequencing all the E. coli and some of enterococcytes. And in 2019, we transitioned sequence to NAMS retail meat sites. The WGS data generated from sites is directly submitted to NCBI. And this allows us in the real time to share NAMS resistant data to public, allow us more rapid for outbreak detection and response. Also, we learned, gained the knowledge of the emerging resistance. Now, I like to give the few examples how we use WGS to support AMR research. First example is detecting novel gentamicin resistant gene in Campylobacter isolated from human, retail chicken, and food animals. The prevalence of gentamicin resistant Campylobacter in the past is quite low. However, in the 2011, there's a sharply increase of gentamicin resistant Campylobacter coli from human and retail chicken. So the initially objective of this study, we wonder what is the resistance mechanism, which genes are responsible for this, sharp increase of gentamicin resistance. We run the PFG and with the two enzymes, all the chicken isolates and human isolates showed identical PFG pattern with two enzymes and also same resistant profile. They're all co-resistant to tetracycline except one isolate. So this data analysis show that the human infection is due to the consumption of a contaminated chicken. Based on the literature, we have designed the primer to detect the gentamicin resistant gene that is called APH family. But the PCR results was have poorly reproducibility. We couldn't get a consistent results. So finally, we decided to do the whole genome sequence. Through the whole genome sequence, we identified the 9 gentamicin resistant genes, and 7 of them are monofunctional, and 2 of them are bifunctional. 7 of them I highlighted red here. Those gentamicin resistant genes have never reported in Campylobacter. And APH2IG, I highlighted in yellow here, that is gene are responsible for 2011 outbreak. The APH family is quite diverse. So you can see here, amino acid identity can be as low as 26%. So this is explain why our PCR didn't work. We had a very poor reproducibility. We have closed the genome and the plasmids for several, this gentamicin resistant Campylobacter coli. They all carry the PTAT MDR plasmids. So they carry the APH2IG gene, but also they carry additional amyloglycan resistant gene as well as the tetracycline TIO gene. So this explains why they all co-resistant to tetracycline. The similar plasmid carry the similar resistant gene has been found in Campylobacter isolated from chicken in China. Now I like to give the second example of our study. Emerging of ESBL 3665 produced Salmonella infantis clone from human and chicken in the United States. Salmonella infantis is a top 6 serotype that causes the human infection in the United States. The ranking has increased over last decades from top 12 to top 6. Here is the CDC's report. Compare the 2016-2018 to 2019, the top serotype with the incidence. As you can see, except the Salmonella infantis, all the top serotype has decreased in the last few years. However, Salmonella infantis has increased 69% the incidence. This is really significant. Salmonella infantis also has increased the prevalence from the retail chicken. And in the 2014, for the first time, we have identified the Salmonella infantis that carry CTX65. And also the increase we see in the human isolates and the chicken seca sample. So we sequenced the several of these Salmonella infantis isolated from a chicken ceca sample, retail chicken, and human. All of those isolates carried the Mago MDR plasmids. These plasmids, besides carry the CTX65, they carry many aminogalactosides resistant gene, trimethylprid resistant gene, fluorophenical resistant gene, phosphor A gene, also tetracycline resistant gene, sulforamide resistant gene, and the streptomycin resistant gene. In addition, this clone has the GIA mutation, so phenotypically they also show decreased susceptibility to ciprofloxacin. This clone has widely spread in the US. As I mentioned here, in the 2014, we first detected this clone in Tennessee. By the 2019, every NAMS retail meat size has detected this clone. Let's look at the global level of this clone. It was first reported in South America, Peru in 2010. By the 2020, this particular clone has reported in many countries. In South America, North America, Europe, Russia, and Asia. So this is a great concern. This particular clone significantly increased from 2010 to 2020 in the retail chicken in the US. But we also found this clone in ground turkey and pork chop. And this CTX65 plasmids also spread to other serotypes. And this plasmids is conjugative, spread to the different strain. So this is a great concern because this particular clone showed resistance to 8 or 10 different antimicrobial and decreased susceptibility to ciprofloxacin. And so because ceftriaxone and the ciprofloxacin are drug of choice to treat the Salmonella infection. So those clones show the resistance to these two drugs. Now, I'd like to give an example. We use the long-read sequence technology, such as a backpile, to close the genome and to study the genomic structure of multi-drug resistant plasmids and the virulence of foodborne pathogens. Here, just give the example, the two Salmonella serotype, we have closed the plasmid and genome. The first isolates here is Salmonella typhimurium, isolated from swine. These isolates carried the 3 plasmids. The big plasmids has over 200 kilobase pair, and they carried the 8 antimicrobial resistant gene highlighted in the red, and also carried the 8 mercury resistant gene, heavy metal resistant gene. This plasmid is a hybrid plasmid. The second plasmid is 94 kilobase plasmids, is also hybrid plasmids carry the marker for Incan F2 and Incan FIB. This plasmid is a virulence plasmid because they carried the virulence operon SPV RABCD. The virulence operon has highly associated with the severity of Salmonella infection. The smallest plasmid here is untypable, but it carried the 6 antimicrobial resistant gene highlighted in the red, and 1 disinfectant gene, and also 7 of the mercury resistant gene. In addition to the plasmids, this particular isolates carried the Salmonella genomic iron in chromosome. So in this genomic iron also contained 6 antimicrobial resistant gene and 2 disinfectant gene. So this particular isolates totally carried the 20 antimicrobial resistant gene, 17 heavy metal gene, and 3 disinfectant resistant gene. So you can imagine how difficult to treat such infections. Now let's look at another isolates. Salmonella doubling, this is a plasmid structure, and this is a chromosome, but it's the same strain of the Salmonella doubling. This is a plasmid over 300 kilobase pair is a hybrid MDR virulence plasmids because virulence plasmids has integrated to MDR plasmids. They carry the virulence R-brown, SPV, RABCD. And they also carried the 12 different antimicrobial resistant genes. These plasmids, if you do the traditional typing, you may think that these isolates carry 5 different plasmids. But when we close the genome, we showed that there's a single plasmids. Actually, they carry the 5 different marker of the plasmids here. So look at the chromosome here. The chromosome show that this Salmonella doubling carry the 15 different Salmonella pathogenic ion. They evenly distributed to the chromosome. Salmonella, the Salmonella pathogenic ion involved the serotype evolution and also the pathogenesis of the infection. Now, finally, I'd like to just briefly mention about the application of beta genomic for resistant profiling. This study was led by my colleague, Dr. Daniel Tadesse. This is a One Health approach. We like to use metagenomic to look at the resistant profile from different commodity. The red circle here showed the resistant profile from the surface water. And the blue circle here shows the resistance from the different food animals, including swine, cattle, turkey, and chicken. If you compare surface water and the food animal, they do share, many of them are resistant gene. And also, if you compare the food animal, they also share the resistant gene here as well too. However, each commodity, they have their unique resistant profile. This is very important. I think in the future, the metagenomic probably can give us a much more comprehensive resistant profile from each commodity. This can really strengthen our AMR surveillance program. So in summary, I hope our data has shown you the power of the whole genome sequence for AMR surveillance and research. And the WGS has revolutionized our AMR surveillance program, and our program has been truly transformed from a phenotypic AMR surveillance to genotypic AMR surveillance program. And the WGS can serve as a single assay for the program and supplement multiple methods, save time and money. Finally, I'd like to acknowledge my colleague from MFDS Center for Veterinary Medicine. They have been working so hard in the last 20 years to continue improve the NAMS program. And also, I'd like to thank my colleague from other agencies, CDC, USDA, NCBI, and the State Public Health Laboratory and some universities that are funded by NAMS retail bids. They make the significant contribution and for the program and make the NAMS become an excellent AMR surveillance program. Thanks for the listening.
네.